Okay, great. So for our second talk this afternoon, we have Mingjia Zhang telling us about p-adic Shimura varieties.
Yeah, thanks. So I have been studying the geometry of p-adic Shimura varieties, and to bring you to this context, let me start answering the question what a Shimura variety is. So this is a geometric object in algebraic geometry that allows a lot of symmetries. So to construct the Shimura variety, one starts with a reductive group over the rational numbers. And the symmetric space for its real points. So this would be a Riemannian, contractible Riemannian manifold that is a homogeneous space under the real points of P. And then we fix a compact open subgroup of the finite adelic points of P. And we suppose it to be small enough. And then we can write down the locally symmetric space, which is a double coset space. So we first take the product of X with this adelic group, so that now by the right regular action, you have this adelic group on the space. But then we quotient out the relation that the rational points of Gx diagonally on these two vectors. But this is still a very huge space with infinite many connected components. So we write quotienting out the regular action of K on the second vector. So this will be a real manifold with only finite many connected components. And surprisingly, if this pair G and X satisfy certain axioms, that will in particular force X to be a permission symmetric space supporting a variation of Hodge structures, then this locally symmetric space will have the algebraic structure in the sense that it will be the analytification of the complex point of an algebraic variety defined over a number field. So in these situations, if we look at the power of these algebraic varieties, labeled by the compact open subgroups, this will be what is called a Shimura variety. And then the geometry as well as homology of these spaces have been an interesting topic to people from different areas, including representation theory, number theory, and differential geometry. And one of the reasons is that now if you pass to the inverse limit of this tower, this is a scheme over this number field, and then you can base change it to the algebraic closure of the base field. Then this object has a lot of symmetry. On one hand, it admits the action of this huge adelic group, and on the other hand, it has the action of the absolute Galois group of the base. And these two actions commute. So now if you're interested in, for example, the Langlands program, you would be interested in studying the Étale homology of this space, which is a representation of both these two groups, while the Langlands program predicts that there should be a correspondence between the irreducible Galois representations and certain automorphic representations of this adelic group. So the cohomology of the space will be a natural test ground for this Langlands philosophy. And let us do an example that is familiar to many people and also which is the starting point of the Langlands program, namely the modulator. So where you can take the group G to be GL2 and X to be the union of the complex upper and lower half plane with R points of G acting by Mobius transform. And for the group K, we can take the principal level defined by the kernel of the reduction modular M map on the Z hat point of GL2. So where Z hat is the completion of that. Say for an integer, at least 3. And in this case, The locally symmetric space will be the complex point of the modular curve at level K. And it happens to have the modular interpretation that the space will be bijective to the set of isomorphism classes of elliptic curves over C together with a trivialization of their end torsion points. So recall that an elliptic curve is a smooth projective curve of genus 1, and its complex point would be just a torus of real dimension 1, and it's in particular also an abelian group whose end torsion points is abstractly isomorphic to Z mod n to the 2. And surrounding the modular curve, you have heard of many famous theorems and like Shimura relations and modularity type of result, and these are shadows of the long lens philosophy with a specific example of Shimura varieties. And now more recently, progress have been made in studying in the long lens program by studying these Shimura varieties as p-adic analytic objects, by which I mean that if you look at this algebraic variety defined over the field D, you can fix a rational prime and choose a place of E above it, and phase change this algebraic variety to the completion of the base field at this place, and then attach to it an analytic object in the sense of p-adic geometry, for instance, in the sense of adic spaces of Huber. Then you get a geometric object whose underlying topology is much finer than the Zariski topology on the scheme, and which is also more suitable for doing p-adic analysis on them. But via comparison theorems, their état homologies remains the same. So you can study the geometry of these objects and extract information of the original ones you're interested in. In particular, if you pass to the infinite level, so which I will denote by S without a subscript, and view it as an analytic object, you can construct a so-called Hodge-state pure morphism on it. So this is a analog of the complex period map, with target being a flat variety attached to G and a suitable parabolic subgroup determined by the Shimura datum, viewed also as an analytic object. So this is this is an analog to complex period morphisms in a sense that if you would be in the complex case, then the analog of the infinite level Shimura variety would be just the symmetric space itself. And then on it, you can look at the Hodge filtration of on the Durand homology of the universal elliptic curve it parameterizes. And at this infinite level, the Durand homology is tautologically trivialized. And then therefore, this filtration gives you a map, was the complex point of P1, which parameterizes filtration of this form. And the P1, this projective line, is the corresponding flat variety in this case. And in this p-adic setting, we look at not the Hodge filtration on the Durand homology, but instead the Hodge-Tate filtration on the état homology of the universal object. And again, at this infinite level, the état homology is tautologically trivialized. And therefore, so in this particular example, you get a map from the p-adic modular form, p-adic modular curve to the a p-adic version of the projected line. And this kind of construction you can do in to general Shimura varieties, even those without modular interpretation. And later it was discovered in the process of constructing a geometrization of the local Lorentz correspondence that this analytic flat variety can be interpreted as a moduli space of modifications of the trivial G-tossers on the so-called Van curve. By projecting to the moduli bundle, you get in particular a map from the flat variety to 1G. And this kind of picture has So this is the classifying stack for G-tossers on the so-called Buckman curve. This kind of picture has been helping to study the geometry of the Shimura variety in the sense that this part, the right-hand side, is purely local, that it depends only on the information of the reductive group base change to QP, and hence the geometry is much simpler. And you can study the geometry of this thing by studying the local counterparts and as well as the fibers. And in this context, it's expected and conjectured by Peter Schulze that there is another object. So the Shimura variety itself is global in the sense that it depends on the reductive group over the rationals, which is a global field. And it's conjectured that there is some object fitting into a Cartesian diagram like this, which captures the global but away from P information of the Shimura variety. And I denote this object by IGS, which stands for Igusa because of its relation to the classical Igusa varieties. And constructing this kind of object have been the interest of my studies. In my thesis, I constructed such objects for Shimura varieties that are moduli spaces for polarized abelian varieties with extra endomorphism and level structures, while currently, jointly with Van Hoften, Daniels, and Kim, we're trying to generalize to Hodge-type Shimura varieties, which is a larger class of Shimura varieties that do not have modular interpretation. And just to finish my talk, I want to say that this is a new perspective of understanding the geometry of the Shimura variety by saying that it can be expressed as a phi product of its P part and away from P part. And hopefully we'll apply this geometric result to understand the cohomology of the Shimura varieties, and in particular deduce certain vanishing type of result on their cohomology with torsion coefficients. Okay.
Thank you. Questions?
So the Archimedean analog of the Hodge-Tate tree map for a more general group, should I think of that as like the embedding of a non-compact symmetric space into its compact?
Right. The Archimedean, the general Archimedean picture is the so-called Borel embedding, and that's all. Yeah. Okay.
Basic question. So what level structure does this SEVN carry, and also this equals up?
So here I'm passing to really infinite level. So you can think of it as the inverse limit along all the compact open subgroups of SEVN1. And then correspondingly Igusa, but for the Igusa stack, but it does not have the P component.
Okay, so like it no longer has any like level structure.
Or with infinite level.
Okay.
Can you tell what this EGS is in the case of
Okay.
GL2?
So in the case of GL2, I define it. So first of all, as an this is as an object. This is a so-called V stack. That is an analytic stack with test objects being projective spaces. But apart from that, apart from what the test objects are, so this is a stack on perfected spaces in characteristic P. That sends a pair R plus to the groupoid of elliptic curves over R plus mod P, but up to isogenies, P power isogeny. Power isogenies. Depends on what do you understand as the moduli problem of the Shimura variety. But then, yeah, more technically, I still have to do a stackification of this construction.
Sorry, so earlier, was your assertion that you're able to construct this IGS in the general PEL case?
So more precisely, it's PL type A and C in the classification of Kottwitz, and with some additional assumption on G at P.
Okay, so in that situation, are you getting like sort of a PEL style moduli description of IGS, or are you just constructing a geometry?
I have a moduli interpretation, and which is very similar to the formula I wrote down there. So I look at isogeny, group height of isogeny classes of abelian schemes with extra structures.
So this object being over ZP
This object.
or just OP?
So it's more like parallel to G, so which means that it has an absolute base over FP.
So there's no map.
So this is, so in the language of diamonds or V-shapes, you could think of them as living overs, but FP. So, which means that their test objects are really all perfectoid spaces in characteristic B.
But there's extra map to VP, natural
To what?
to VP.
No. Because yeah, these objects, you do not prescribe a lift of them. Something.
Could you also tell more about the map from the flat variety to G?
From flat variety to G, yes, I can. So I did a silly thing, but
That's not the one.
okay. So the flat variety can be understood as a moduli space of modifications of G bundles. So these are G bundles on the so-called Van Denker. And this one is trivial. And this interpretation is by Uvill-Laszlo gluing. And then once you have this identification, you can send a point of it to just this modified bundle.
You said you're interested in some like homological vanishing applications. I was just wondering, like, is this Iguza stack, like, does it make sense to talk about like its model cohomology, and like, can you say something about the model cohomology of that, or is this sort of yeah?
Yes, it makes sense to talk about model.
What can you say something about the model cohomology? Just the Iguza stack itself? Or is it...
Yeah, this question makes sense. And then the way you study it by this picture is that so imagine you want to study the cohomology with FR coefficient. You can use the Leray spectral sequence and push it forward to G. And there, so what you can use, which is very powerful, is that there, if you localize at some L parameter, some prescribed L parameter that is generic in a certain sense, then you will know without doing some anything extra, you will know that it will be supported only on certain stratum of G. And this is already some type of vanishing. And if you understand the sheaf, the push-forward sheaf better, for example, you know that it's semi-perverse or perverse in the case where the Shimura variety is compact, then you would even know the cohomology degrees that concentrated.
Sorry, what is the relationship between this diagram and the local models constructed in the AJLR paper?
So the local model is like an integral model of the flat variety. And we also have, so we have an integral version of this diagram, although at P, what we do is not to replace, to get this integral version of the diagram, what we do at P is not to use the local model, but instead use a modelized stack of p-adic Shtukas.
All right, I'm gonna put a pin in the question. Thank you very much.